Okay, I'm going to walk through the Jupyter Notebook for this week. I combined the Fashion MNIST Feedforward neural network with the convolution neural network and the convolution neural network with dropout. And I've tried to put it all in one to make it a little bit easier. So the first thing here is understanding that, let's do this, edit, let's clear all outputs, change the runtime. Okay, good, T4 GPU, save, okay. Now, what we're gonna do here is first, this is Google Colab, as you guys know. There's a code block and a text block. You can type things in the code block, and then you can execute it, Shift Enter. Okay, I'm not a robot. Traffic lights, no problem. Okay. And so we're running this code block, as you know, and there's also a text block here, and you can just say like hello, right? So that should, everybody should be familiar with those two. Now here we are going to use a particular, we're going to import the TensorFlow, and inside TensorFlow we're going to use Keras. Here's a couple of things: sequential, dense, flatten, and so forth. Import numpy as np, import matplotlib pyplot as plt. These libraries should look more and more familiar to you as we go through this class. Okay, looks like everything is installed well. Now, the data set that we're going to use is Fashion MNIST. As you know, there was MNIST, which is a handwritten digits. Fashion MNIST is a little bit more difficult because these are pictures of different types of clothing. And but you know, nonetheless, it's still 28 by 28 pixels, and you can look at, you hit this link for more information. But this data set contains 60,000 grayscale images in 10 categories, right? 60,000 will be used in the training and 10,000 in the test set. And you know, this is, you know, the full data if you want to take a look at that. Now, what's really nice about TensorFlow is that in this one line of code here, fashion MNIST equal keras.dataset.fashion MNIST, we are going to read in all that data. So fashion MNIST load data, we have the training images, the training labels. So this is like X and Y in the training set. And then you have test images and test labels. This is like X test and a Y test. So in one line of code, you'll see right here, well, two lines, you're really reading in all this wonderful data here. And this is the one that we're going to use, and we're going to build some neural networks to see if we can classify these things. Okay, so let's take a look here. First thing is to remember that when you flatten out one of these pictures, 28 pixels by 28 pixels, that's 784. So you make a vector 784. And this is going to be important whenever we do the feed forward, the standard neural networks. Okay, so the labels here are integers ranging from 0 to 9, but associated to each one of these labels, you can be a t-shirt, trouser, pullover, dress, coat, sandal, shirt, sneakers, bag, and ankle boot, okay? So we are using this right here. This class name is a list, and this is actually the name for, you know, each of the categories of these pieces of clothes, all right? So the first thing to do is take a look at the train images. So let's take a look at the shape of that. What are the dimensions? It's 60,000 rows, and then 28 by 28. So, you know, you can think of this as this three-dimensional sort of, you know, cube. The other way to think about it is in each one of these dimensions is a 28 by 28 image, okay? Now let's also look at we just looked at the train images, or the train X. Now let's get the train Ys, and we can see here that it's an array, and here's a couple of samples, 9, 0, 3, 0, 5, so forth, right? Data type unsigned integers with 8 bits. So this is, you know, this is how it's held. So we can also explore the test data set. We know that 60,000 was trained, then 10,000 was test. So when we look at the shape of the test, 10,000 and then 28 by 28. Excellent. And we can also look at the test labels. So these are the true labels of the test. This is what the test is what we're going to try to make a model using the training data, and then we're going to test how well we make predictions on the test set. And in the test set, you're supposed to only use once, and then that way it's unbiased. Okay, an unbiased model, unbiased estimate of how well you did when you get the accuracy. but a lot of times people will do that a couple of times. Okay, so let's look at one of these pictures. So plot.figure, image show, train 0, training images, that's the first one, it starts at 0. And then we have a color map, and this is a binary color map. You're also going to plot the color bar next to it, and then we're not going to have any grids. So when you plot this, you can visually inspect that in fact this is one image. And if you want to change this, you can change this to, this would be the second image, shift enter, and this could be the third image, right? And so forth. And you can go all the way up to 59.99. Okay. So this is, and if you try to do 60, there's no more 60 because it started counting at 50,000. I'm sorry, at 0, right? So there's nothing. So you should feel comfortable with, changing some of these, which example are you looking at? So even when I'm hovering over this, it even says this is shaped 60,000, 28 by 28. Because Python starts counting at 0, that's why we go 0 to 59,999. Okay, so that looks nice. Now this is telling us that the values of these pixels go from 0. 0 is white, and then when you go 50, 100, 150, 200, and then 250, 250, 255. 255 is the darkest color here, right? So, this kind of looks like a boot. And now let's do something. This is normalization. So many times in, machine learning and in AI, will re-normalize the data, and they usually tend to keep it sort of close between sort of around 0, so between 1 and -1. And an easy way to normalize the data, because we know the maximum value is 255 for any of these pixels, as per this example here that you can see. If you divide every observation, so remember there's 60,000 and it's 28 by 28. So if you divide every one of those pixels by 255, now what you've done is you've normalized this. So we'll take a look at this. Notice that this scale, the color bar, is going from 0 to 1. Before it went from 0 to 250 or 255. Since you divided all the pixels by 255, now it goes from 0 to 1. And this is a normalization technique. There's other normalization techniques. One is like z-score, where you take each observation, subtract out the mean divided by standard deviation. There's also what you can do is take each observation, subtract out the minimum divided by in the denominator, you'll have max minus min. So that's also another way to scale, observations and data. And you see it quite a lot, in this type of literature, because what happens here is that if you get your data sort of in a well-behaved range, let's say -1 to 1, then whenever you're trying to solve for the weights, it's a little bit easier and it's a little bit faster. Okay, now in this right here, you're going to create a plot. The size is 10 by 10, and you are going to go and put 25 of these pictures. For I in range 25, you're going to start plotting each one of these pictures, and you're going to get rid of the X ticks and Y ticks. Those are just the labels, the notches on the X and Y. You're not going to print the grid, and then you're going to image show the training images, and then you're also going to put the class name. Notice this is training labels. Remember, training labels is an array, so you're going to get the observation array. It's going to be between 0 and 9. And then once you get that 0 and 9, you're putting it inside here, and now you're going to pick out the class name. So this is actually going to give you a name, whether it's t-shirt, top, trouser, pullover, dress, and you're going to put that name inside your X label. So here's your picture. There's 1, 2, 3, 4, 5, and then 5 down, so that's 25. Each one of these, it has a picture and then the label, the actual name. So ankle boot, t-shirt, and so forth, right? So these are the actual pictures and their labels that are correct in your training data. So it's always good to visually inspect your data before you get started to do anything, just to make sure that everything looks pretty good. Okay, now we're going to set up the neural network architectural structure here. Okay, so the way that this is set up is that first you create a function, and this function is called baseline. How do I know this function? Because you have the DEF defined, and then the function name. This function, as you hover over, it also says function. It doesn't have any inputs. So basically what you're going to do is you're just going to run this. When you run this function, there's no input, so there's no input variable, but what you do return is the model. So here, when you run this function, you have this model equals sequential. Recall that sequential is a class, and you are instantiating a model from this class sequential. And this, sequential class creates this neural networks. And here's an example how it does that. So model, now we're going to add a layer. Okay, this is a neural network. First, we notice that the input dimension is 28 by 28, okay? And then you have this flatten. This is very important because what you're doing is you're taking one of those pictures or images. We know it's 28 by 28, but then we're going to flatten it. So this is going to be 784. So think of it as a numerical vector of 784 by 1 or 1 by 784. And basically what this is a very long vector of just numbers. And inside the numbers are the pixels from 0 to 1, okay? So model add, we're going to add this flattening from the input. So think of the, this is, x1, x2, x3. This is the data going in. Then you have this dense layer, 128 nodes. Okay, so this is the first hidden layer. It has 128 nodes in there. Activations is rectified linear unit. We've covered that. And then you have another layer. This is the second hidden layer. Now this has 256 nodes in there. And notice that it's very easy if you want, 255 nodes or, whatever, you can easily change it here. If you wanted to add another layer, it's very easy. Here's, I'm adding another layer to this neural network. So, it could go 128, 256, and then back to 128, whatever you want, or 128, or you want 64. So what's interesting and very easy is that Keras makes it very easy to create a different type of neural networks. Now, the last layer here is dense 10, why 10? Because we have 10 categories of those pictures, those different types of clothing items. And now we have softmax. And softmax is very important. As we know, softmax casts the final logits into a probability. And so the way it works is that the classification that the model predicts will be that whatever that category of clothing that has the highest probability. And softmax ensures that the last layer generates a probability over each of those classes. So for example, if it says t-shirt and the probability is like 0.8 or 80% t-shirt, then that's probably, what it will predict that t-shirt. We'll go through it one more example so you can see that, but it's very important to start having some intuition on what are these. So this is your input, okay? These are your two hidden layers, two or more hidden layers. That's a deep neural network. So we have deep neural network here. And then we have the output layer, which is going to make the predictions. And it's going to predict. Remember, we have the truth. So we know what categories those pictures are. And if we start running this, initially what we'll see, it will make an error. And so what we do is we take that error and we back propagate it through this neural network. And we calculate and adjust the weights, right? These are the parameters that we can move around and adjust to make the model better, right? Now, the other thing that we didn't cover here is finally, how are you going to compile this model? So the loss function is sparse categorical cross entropy. So we specify this function because what we're doing is in the y variable or the target, we're putting not the actual the text labels. It's not t-shirts and shoes and sandals and so forth. It's actually the number 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So this loss sparse categorical cross entropy allows us to put the predictive variable y actual numbers 0 to 9. The optimizer is Atom. We know we're just going to always use Atom, but there are many other different types of optimizers here, including momentum and so forth. But we're going to use Atom for the majority of this class. And then what we care about is, capturing the accuracy. So when we hit this button here, we are creating this function, but we're not running this function. That's very important. And this think of it as the architectural structure. We've laid this down. What we want is this type of neural network, right? So the input is flattened. There's two hidden nodes. And the first hidden layer has 128 nodes, and the second hidden layer has 256 nodes. And then the output layer, where it has 10 nodes, and then that's what's making the prediction because we have a softmax activation. So now we put this in memory. You got to get a nice green check mark here, and now we go onwards. Okay. Now, what is very important is at this point, what we've done, we have put this model, we've created a model. Now let's make sure that we look at this model. So we are going to call the function that we created earlier, baseline model. So notice this is baseline model. So model is equal to baseline model, and then we do model.summary. So we're going to take a look at this model. And this is actually very, very important to just stop here for a second and think about this. Okay, so the first, this is the x1, x2, x3. The input data is coming in. There's 28 by 28 is 784. So that's the dimension of the input data. Now the data goes in. How many parameters are there? There's no parameters on the input layer because that's just the data, right? Now the next layer is that hidden layer. The hidden layer has 128 nodes. Okay, now from the input data to the hidden layer, those are, we have all those arrows that are pointing, right? And how many parameters do we have? And this is actually very important. You know, it's good to stop and think about how many parameters. So if we do it the wrong way, right, what we'll do, here, let me clear out and get my calculator. So if we do it the wrong way, I'm gonna try to match these, okay? So here's code. And let's do 784 multiplied by 128. Let's see if this works, if I can run that. Okay, so if I just do the 784 data points coming in, multiplied by how many nodes, 128, I have 100,352. Now, if I look at this, I'm like, oh my goodness, hey, what's going on here? I made a mistake. You can't just multiply the number of observations, 784, going into your neural network to hit your first hidden layer, which has 128 parameters. No. So what you're missing here is actually the bias. So we need to add back the bias. So for each one of those nodes, you have one bias. So when we notice that we do 784 times 128 plus 128, then we are matching the 100,480, which is perfect. Now let's do the next one. Okay, so we have 128. Now now this becomes output to the next layer. The next hidden layer has 256. Okay, perfect. So now let's calculate the number of parameters. So 128 multiplied by 256. If we do that, we've got the parameters, but we're off. We're a little bit off here because notice the parameters are 33,024. So what are we off? Once again, we forgot to add each of the biases back. So we have all the weights multiplying the output from the hidden first layer, but we need to add back all the bias terms where there's 256 bias terms associated. So when you do this, 128 times 256 plus 256, then you get 33,024, okay? And then I'll let you guys do this, but basically it's 256 times 10, which is 2,560. And then as you know, this is 2,570, where it happened to the 10. Well, there's associated to each of these outputs in these predictions is a bias. So you need to add those back. So it's 2,560 plus 10, which is 2,570. So it's actually very important to just stop here, really understand that, you know, add up all these parameters that right here, which is this column, and just, you know, make sure that you feel comfortable with, you know, what this looks like. And I think it's a good way to sort of test if you really understand what's going on with this neural network. Okay, just to summarize, the input was 784. The first hidden layer had 128 nodes. The second one had 256 nodes, and the last one had 10. Okay, now next up, let's do model fit. And this is where all the action happens. So history equals model fit. We're going to do that because we want to take some of the data out of this, in particular the accuracy and also the loss. So we put the data in, fit train images. This is the training set X. It also gives you the dimension, 60,028 by 28. Training labels, these are basically the numbers, right? For each one of these, you have either a 0 or up to a 9. The batch size is how many of these are you taking at the same time? So 128. Epochs is how many times you're going to go through the 60,000 data points. You're going to do it 10 times. You're going to shuffle the data every time, and the validation split is going to be 10%. So every time you go through this data, you're going to take 6,000 of the data, and that's going to be your validation, and the 54,000 is going to be your training. So you're going to train it, and then you're going to test on the validation set, and then After you do that, you're going to shuffle, and you're going to do it again and again and again. So when I hit this is where all the action's happening. You get the first epoch. Remember, we're going to do 10 epochs here. It shows the accuracy 73%, losses 0.79, right? Notice the loss is falling pretty rapidly, which is great. You want the loss to go down. You want the accuracy to go up, right? Validation is the 10% validation. So remember, you have 60,000 data points, and you're basically but you're taking that and you are reserving 10% at each one of these steps. So okay, so it's finished. So the accuracy is 91%. That's and the loss is 0.23. Okay, great. And then the validation accuracy is 0.88. Okay, with a loss. So this gives you a pretty good idea where you're going to be at whenever you do the test data. Remember, this is all training data. Okay, now we run this, and then we're going to run this. So we're going to actually take a look at what this looks like. So here we have two lines. One is a blue line, which is the training accuracy. Notice as we're doing it, the training accuracy goes up, and the validation accuracy, which is the orange line, goes up, but not as much. So we're starting to sort of overfit, meaning the training accuracy is above 90%, but the validation accuracy is sort of still hovering around 88%. Again, you can look at the model loss. You want the training to loss to go down over time. And then this is as you're fitting the model. And then you also want the validation loss to go down, which looks okay. But notice that they're starting to diverge, because what's happening here is that you can only get so much out of this particular structure, the feedforward neural network. Now, here is an example where you're going to do testing how robust is your model. So presumably your model that you created has never seen this data in the test, right? So that's the test images. Okay, this is the 10,000 data points that are in the test set, and then the test labels. Okay, now when we run this, we're seeing how well it does, and the accuracy is about 88%. Recall that this was sort of around 88% if you look at that, right? So this validation accuracy is pretty good predictor of what's it's going to look like in the test, which so keep that in mind. Okay, so the test accuracy is about 88%, which is not bad. If you want to make a prediction, you can now use your model, right, and make a predictions, and you can see what the first prediction is. These are going to be probabilities, right? Because we went through a softmax, okay? And then we're going to pick out which one of these arguments did it figure out. So it was 9. So it's predicting that it's a 9. So let's take a look at this. The current class name for the test label, the first one, is ankle boot. Now, what we did was we make the predictions, and we picked out which class it thought it was, and it also predicts 9, so it's an ankle boot. So this did it correctly. Here we are going to plot some images. I'm not going to go through all of this. You can just look at the results, which is actually very nice. What it does is it takes each of the images, and it tells you whether it's what's it predicting, and then what it really is. And it's blue if you've got it correct, and it's not blue if it's got it incorrect. So here's an example. This is actually looking at the predictions, so we can actually see they actually put the names here, and it says ankle boot with a high probability, 99%. Okay, but it does have small probabilities here for sneakers and sandals. Now here's one that it didn't do well. So image 222, which is the 223rd image. It says that it thinks it's a code, 29%, but that's actually a pullover. So when you actually look at the values, the probabilities here, notice that the coat, it's supposed to be a pullover here, but the coat is a 1, and it colors red when it's incorrect. So that's a really nice visualization. But this is the last layer that after the softmax, now you have probabilities. Okay, so here's an example where you can kind of look through, and you can see how well. So the ankle boot, it did well. This did well. Okay, and let's see if it did. Okay, here's it says it thinks it's a pullover, but it's actually a coat, right? Here's another one. It thinks it's a sandal, but it's actually ankle boot. So you can sort of look through some of the data this way. All right, now the next thing that we're going to do here is actually redo this, but we're going to use a convolution neural network that we covered in class. But we're not going to use dropout here. We're going to do the dropout later. So here we'll just add some libraries that we need. Again, this time we are going to reshape the X train and the X test. So we need to keep it in that dimension. So we're going to leave it at 28, 28. Okay. We're not going to flatten it out. Now, notice in here we are going to define a baseline model that's called CNN, model sequential. So from the sequential class, we're going to instantiate the model. And then we're going to start adding. Now, look, notice this. This is add the convolution 2D. So we're going to add 256. Okay, these are feature maps. And we're going to use a convolution 3 by 3. Remember, these are where the parameters are sitting. In addition, so that's 9 plus the bias term, which is going to be 10. Padding is going to be the same. So as you take that filter or the kernel across the image, right, you're going to create a new feature map. That feature map is going to have exactly the same dimensions as your image. So if the image is 28 by 28, the feature map is going to be 28 by 28. This padding equals same will ensure that your new feature map also has the same dimensions as your original image. Activation Liew and the input shape 28 by 28 by 1, so it's actually giving the image inside there. Next after that, remember in the convolution layer, we know where the parameters are coming in, but for each of the feature maps, there's 256, there are 256 filters or kernels associated to each feature map. Plus, so that's 3 by 3, so that's 9 plus 1. That's so there will be 2,560 parameters here. Okay. Now, next we have max pooling. The pool size is 22, so you do that for each of the feature map. Here in max pooling, as we went through in class, all it is basically taking the max value out of that 2 by 2 matrix for the pixels, and there's no parameters here, okay? And then we have another layer with the convolution 64, so now there's going to be 64 feature maps with 64 kernels, all right? Same thing, padding and Liew, and then max pooling. Then we're going to flatten it all out, and this is where it goes into the neural network. So this point on, you should be familiar. This is one hidden layer, 128, which is the number of nodes, activation Liew. And then now we go to the final output layer, which is going to be dense, 10, activation softmax. Remember, it has to be 10 nodes at the prediction level because you have 10 categories, right? Model compile, loss, sparse, categorical cross entropy, optimization atom, accuracy, and so forth. So now we put this function in. Okay, perfect. And then we look at the summary of this. Okay, so again, look, and can you interpret these parameters, right? Why 2,560? Well, if you go back here, you say, okay, I got 256 feature maps. Each one of those feature maps has a kernel. We know the kernel is where the parameters come in. It's size 3 by 3. So 3 times 3 is 9. Okay, those are the parameters plus the bias terms. That's 10. So 10 times 256 is 2,560. So that's how you get these numbers. And you can go through and sort of figure out and argue to yourself how we can get all these parameters. And it's not a bad exercise to try to do that. Again, once we have the model, we're going to fit. Here comes the data. Batch size 128, so this is how much we're going to take at a time. We're going to go through the data 10 times. We're going to shuffle it and validation split. So you're going to take the training set and split it into the training and validation, right? We haven't touched the test set, so just don't get that confused. So remember, we're just using the training set, which is 60,000 images, right? So now we're going through this. 10 epochs. Accuracy is sort of coming along. The loss, let's see if it's going down. Yep, the loss looks like it's going down, which is great. So looks like it's working. The accuracy now is 89%, which is not bad. Validation accuracy 89. Okay, that's pretty good. Just recall that before in the feed-forward neural net was sort of around the 88%. Oh, 91, which is great. 90%. Okay, so we're coming along here, making some progress. As you guys know, the convolutional neural net should do a little bit better than the feed-forward network. That's why the Fashion MNIST is an interesting data set, because recall that in the MNIST data set, which is the handwritten digits, it was pretty easy to do this even with the feed-forward neural network, right? So, it looks like it's coming along. The losses are going down, which is good. The accuracy is sort of creeping up, which is good. And then now it's kind of getting overfit because the accuracy of the training, right, is 95%, but the validation is not sort of creeping up any higher than 91, 92%, right? So here's a last run. It's all the way up to 96%, but this can't get more than sort of 92%. So when we put this, we take a look at the curves. So the training continues to go up. The validation sort of peters around 91, 92. And the same thing with the loss. Notice that as you go more and more through your data epochs, as you run your more and more data through, and you're adjusting the parameters and weights, the training loss continues to decrease, right? Because we're overfitting, and then the validation loss does not. So at some point, maybe you want to do an early stopping here, but this is an example where you're overfitting the data. Okay, and remember, it's very easy to overfit the data with these complex models with lots of parameters. So now we try the test set, and it's sort of like 91.75%. Okay, now let's add dropout. So in order to add dropout, you notice that this is very similar. However, we have this new model.add dropout. So how does dropout work? The easiest way to think about it is that you're sort of dropping out some of the parameters or the nodes, or there are other techniques where you drop out some of the feature maps, right? As opposed to individual sort of data inside a feature map. Some people will drop out the whole feature map. So the idea is dropout is a regularization technique. Okay, so you are trying to restrict the model, make the model work harder in order to try to find a pattern. And so here's an example. Everything else you should sort of look and understand. Here is the dropout. There's a dropout over here, and then over here. You can have a dropout in the neural network, the feedforward neural network, and you can also have a dropout in the convolution areas. But the idea is that you sort of remove half of the nodes. You're just sort of dropping them out, making it more difficult for the model to find the relationships, okay? And then here, we're going to call the function, and then we're going to summarize the function. You can take a look inside here. And then what we're going to do is fit this, okay? Okay, looks like we have 20 epochs here. So it might take a little bit of a while. I'll try to speed this up in the video if I can figure that out, or I'll just cut this part out. We'll see. Okay. Feel free to play around with the parameters and so forth. But, now you can go get your cup of coffee while your convolutional neural network fits the data with the added dropout. Okay, so when we look at this, this is the last one. The accuracy is 92%, all right, with the training data, and the loss is down to 0.2. And the validation accuracy is 92%, which is nice. Validation loss is 0.2. Okay, so that looks pretty good. And then if we look at the curves, the validation training is nice. It's sort of converging here. And then also the training validation is sort of getting down there. So that looks pretty good. And so with dropout, we can get up to like 92.41%, which is not bad. So, you can keep changing the parameters and trying to find better parameters and different specifications with the architectural structures and so forth, and try different dropout rates. But, basically the idea here is to just give you a flavor of what it's like for a feedforward neural network, and then for a convolutional neural network, and then, just one regularization technique. There are many for a convolutional neural network with dropout. Okay, so with that, I will stop the video.